So this will be the 6th lecture, electrochemistry. We can have a problem solving session if you need later. In previous class we have told about how the conductivity and molar conductivity changes as we dilute a solution. So on dilution we saw that kappa, which is conductivity, decreases due to decrease in number of moles per unit volume. However, molar conductivity increases due to increase in mobility. So today we are going to focus on this particular topic, that is how the molar conductivity increases for strong electrolyte and weak electrolyte on dilution. So both strong electrolyte and weak electrolyte, they have a different way in which their molar conductivity is going to increase on dilution. So we are going to study theories for both of them separately. So before that, let's look into what is the difference between a strong electrolyte and a weak electrolyte. So firstly, strong electrolytes. So what are strong electrolytes? Those electrolytes which will completely dissociate are called strong electrolytes. So these are the ones which undergo complete dissociation. And what are the examples for strong electrolytes? Strong acids, strong bases, and the salts formed by strong acid and strong base. So the example can be HCl, a strong acid, NaOH, a strong base, and the salt formed by both of these, that will be NaCl, and other salts which are formed by strong acid and strong base, for example KCl, KNO3, etc. All of these will completely dissociate into their ions once they are in solution. Second is weak electrolytes, and they will be just the opposite of strong electrolytes, which means they will not completely dissociate into ions on dissolution. So they do not undergo complete dissociation. So if strong acids and strong bases are a part of, or they constitute strong electrolytes, then weak electrolytes will be weak acids and weak bases. So an example for weak acid is acetic acid. So that can be taken as an example. And weak base is ammonium hydroxide. Okay. Now if we try to plot their variation in the molar conductivity during dilution, we get a plot like this. Okay. Let's take lambda m as y-axis, root of concentration as x-axis. So if you look at here, if you go from right to left, we see that here concentration decreases, which means this is the direction in which dilution increases. Okay, since concentration increases from left to right, from right to left, it is dilution that is being increased. Okay, so the plot for strong electrolytes is a line, straight line with a negative slope. Why? Because on dilution, that means on going from this to this, their lambda m value should increase. If you look at this, initially at this concentration, they had this much molar conductivity. As we decrease the concentration, that means on increasing dilution, their molar conductivity kept on increasing. The value is increasing. At some infinite dilution, that means when concentration is almost zero, at this point we cannot actually determine how the change is, so we just represent them by dotted lines. But anyway, in general, there is a linear increase in lambda m as there is increase in dilution. Nextly, for weak electrolytes, it is a different graph. Here it was linear for strong electrolytes, but for weak electrolytes, we see there is an exponential increase in the molar conductivity on increase in dilution, which means if you increase dilution, it is going to increase exponentially. Okay. So there is a sharp increase in case of weak electrolytes. Now to explain this, we are going to study two different theories. So firstly, let's write this is for strong electrolytes and this is for weak electrolytes. So the theory which will validate the slope or this particular graph for strong electrolytes is Debye-Huckel-Onsager theory. And the theory which will explain this variation for weak electrolytes will be Arrhenius theory, or it can also be called as Ostwald's dilution law. Ostwald's dilution law. So firstly we are going to see Arrhenius theory, that is for weak electrolytes. So according to Arrhenius theory, since the weak electrolytes do not undergo complete dissociation, they will actually be in equilibrium with their ions. So for example, let's consider a weak electrolyte, acetic acid. So acetic acid will actually dissociate into CH3COO minus and H plus. And we know this dissociation is not complete. So according to Arrhenius theory, acetic acid will be in equilibrium with their ions. We represent it like this. Now we need to draw an ICE table for this. So you will be studying ICE table in detail in equilibrium chapter. But just for using it here, I'll explain it to you. So ICE table, we usually use it for concentration terms. Okay, so ICE table, you have to use it for concentration only. Okay, so in this I represents the initial concentration. Initial concentration, you write it as I. Okay, and C represents the change in concentration. Whatever change is happening, that will be represented as C. Finally, E represents concentration at equilibrium or the equilibrium concentration. That is E. This will be your ICE table. Now let's write what are the concentrations for each of these. That means for acetic acid, acetate ion and H plus ion. So initially when you take acetic acid, its concentration is going to be C. Right, let's say it is C concentration. And before dissociating, the concentration of ions would obviously be 0. So initially we have 0 acetate ions and H plus ions. And after dissociation, there will be a small change or a small decrease in the concentration of acetic acid and increase for these both ions. Right. And that change will be, so the change will be how much of the original concentration is dissociated. Suppose if I give a name alpha as the degree of dissociation, so C times the degree of dissociation, that will be C alpha is the change, which means your acetic acid will have a decrease by C alpha concentration. Now how much will acetate anion increase? If 1 mole of acetic acid is used up, we see that 1 mole of acetate anion and 1 mole of H plus is produced. That is as per the stoichiometry of this equation. So if C alpha is being used up, then C alpha of anion and C alpha of cation should be produced. So there is a decrease in concentration of acetic acid by C alpha and increase in concentration of the two ions by C alpha. Now what is the equilibrium? Equilibrium will be I minus C. So initial minus the change, that will be the concentration. Right, so initially it was C, but C alpha was used up. So at equilibrium we will be having C minus C alpha. In case of the ions, initially it was 0. So at equilibrium they will be just as the same as the change produced. That will be C alpha and C alpha. So this is how you write an ICE table. Initial concentration, change in concentration, and finally equilibrium concentration. And in here note that alpha represents degree of dissociation. Okay, so alpha represents degree of dissociation. Now, how do we write the equilibrium constant K for this particular reaction? We know equilibrium constant will be concentration of product by concentration of reaction raised to their stoichiometric coefficient. So here it will be concentration of CH3COO minus into concentration of H plus divided by concentration of CH3COOH. Now from the ICE table we know what are the concentration of all of these. So we can replace it. What is the concentration of CH3COO minus? It is C alpha. For H plus also it is C alpha, and in the denominator for acetic acid it is C minus C alpha. Now from this I can actually take C common, right? If you look at the equation, C is common in the denominator. So the numerator is going to be C square alpha square divided by denominator. I'll take C as common, so C into 1 minus alpha. So there is common C, I can cut it, cancel them, and then finally I will have C alpha square divided by 1 minus alpha. So this is the equation for equilibrium constant K. C alpha square by 1 minus alpha. This is one equation. Now alpha is actually the degree of dissociation. It is actually a very small value. Okay. It is usually a small value, but in cases when alpha is very much less than 1, and alpha is very much less than 1, in that cases we can consider 1 minus alpha is approximately equal to 1. That means alpha will be negligible. If 1 minus alpha is approximately equal to 1, that means the denominator is 1. So what happens to K? Eventually K will become equal to just C alpha square. Here alpha square we are not going to neglect it. Only the denominator will be neglected. Okay. So K will become equal to C alpha square. Now the purpose of doing this is to find a simple equation for alpha. So what is alpha from this equation? Alpha will be equal to K by C. Alpha square is K by C. So alpha will be root of K by C. So that is the equation for alpha. In order to get this equation, we have considered alpha very much less than 1. Or in those cases where alpha is very much less than 1, there we can use this equation. In other all cases, we have to put it into this equation and find alpha. That will actually involve solving a second degree polynomial, which will still be okay, but in this way it will be a bit more convenient and which can save time, but only possible if alpha is very much less than 1. Now let's write what are the terms involved. Alpha, you know it is the degree of dissociation. K is obviously the equilibrium constant. And finally C is the initial concentration. C will be the concentration. Okay. Now from this equation it is clearly evident that alpha is inversely proportional to, how do we differentiate alpha and proportionality sign? Alpha is inversely proportional to root of concentration, which means when concentration increases, alpha will decrease. Now this explains why we have the particular graph for weak electrolytes in terms of molar conductivity and concentration. So you remember this graph, lambda m versus root c. In case of weak electrolytes, we see that degree of dissociation decreases on increase in concentration, or you can say the degree of dissociation will increase on increase in dilution. Okay, so dilution means there is a decrease in concentration. So since there inverse proportionality, on dilution alpha value will actually increase. So the graph was like this, right? And hence we have used Arrhenius theory to explain the change in concentration change in conductivity of weak electrolytes with the change in concentration. Okay. The next theory is Debye-Huckel-Onsager theory, which is to explain the variation for strong electrolytes. So we have Debye-Huckel-Onsager theory. So according to this theory, in a solution, when you actually add the electrolyte, which will ionize to some extent or completely. So in case of strong electrolytes, they have to completely dissociate. So they form ions. These ions in solution will actually be surrounded by an ionic atmosphere. So suppose if you have a solution you take and you have positive ions. So this, according to this theory, your ions, if it is positive, they will be surrounded by an ionic atmosphere of oppositely charged ion. So if it is positive, it will be surrounded by negatively charged ions. Okay, and if it is a negative ion, it will be surrounded by positively charged ion. And this is called as the ionic atmosphere. This is called as the ionic atmosphere. So now if we do not apply any potential to this system, this ion, the ionic atmosphere will be symmetric and spherical in nature. So you can obviously understand there will be a positive sign which is perfectly surrounded symmetrically by the negative signs, symmetrically and spherically. That is in absence of any potential. But suppose you are giving some amount of potential to this. For example, I am connecting a wire here, okay, and I'm giving a positive potential here and a negative potential here. So obviously opposite charges attract and the negative all will go to the positively charged region and the positive will go to the negatively charged region. That is an obvious thing. But because of this ionic atmosphere, it is not very easy for these ions to move towards the oppositely charged potentials. So imagine if you had a system where the ions were all free, they would quickly move to their oppositely charged species. However, because they are internally also attracted to opposite charges, that means inside also this minus is slightly attracted to the positive charge. So when an external potential which is higher than the internal attraction comes, they have to break this attraction which is there with the internal species and only then they can go to the external potential. So because of that there is a slight lag produced here. So this is called as the asymmetric effect. Okay, this kind of lag is called as the asymmetric effect. And there is one more effect called as the electrophoretic effect. Electrophoretic effect. That is based on how the solvent molecules surround your ion species present in the solution. So that is also somewhat similar to this explanation, but we are not going detail into those theories because what we are interested in here is the Debye-Huckel-Onsager equation for strong electrolytes, not deep into their theory. So let's look into the equation. The equation is very simple. It says lambda m is equal to lambda 0 m minus b root c. So in this, lambda m means molar conductivity. Lambda 0 m is molar conductivity at infinite dilution. So earlier when we drew the diagram, we have seen that towards this particular region we have put only dotted lines, and I told you this is a region of infinite dilution. Infinite dilution means concentration is almost zero. Okay, so this is a point of infinite dilution. This is a point of infinite dilution and we will represent it as lambda 0 m. So this is the lambda 0 m that I am mentioning in this equation. So we get that molar conductivity will be equal to molar conductivity at infinite dilution minus B root C. So root C is obviously concentration, you know that. Now the question is, what is B? B is called as the Debye-Huckel constant. B is Debye-Huckel constant. This is in turn another term, that is B is equal to A lambda 0 m plus B. So this is what B is equal to. Now if you put this into this equation, you will get that lambda m equals lambda 0 m minus A into lambda 0 m plus B whole into root C. Now let's just expand the bracket. I'll have lambda 0 m minus A lambda 0 m root C minus B root C. This is the final equation that you're going to get. Okay, so from this we have already got Debye-Huckel constant B. Now B is actually dependent on the stoichiometry of salt. So B depends on stoichiometry of salt. Of salt means this or electrolyte that we are using. Okay. Now in this equation, A into lambda 0 m root C. This will actually give the changes in molar conductivity due to asymmetric effect. We have seen there are two effects which will contribute to Debye-Huckel theory, asymmetric and electrophoretic effect. Out of that, this term A lambda 0 m root C will be the contributor because of asymmetric effect. And we say that lambda 0 m minus this particular value. Since it is a minus, it causes a decrease in the molar conductivity. So we can say that A lambda 0 m root C is the decrease in molar conductivity due to asymmetric effect. Okay, so this is decrease in lambda m due to asymmetric effect. And B root C will be, again since it is a minus, this is also a decrease, but it is going to be the decrease in lambda m due to the second one, that is the electrophoretic effect. Now if you look at this equation, that means the above one, you'll understand that there is a linear relationship between lambda m and root C. So this can be considered as y is equal to, let this be C, this be minus m into x. Okay, so we can understand that, or you can simply write it as plus mx and put m is equal to minus b. C plus mx. So this is the equation for straight line, y is equal to mx plus c. Of that we find m is equal to minus b, where x is root c, y is lambda m, and that is what we have already seen from the graph. The graph had straight line with a negative slope, and the intercept is obviously lambda 0 m. So lambda m is the y-axis, root c is the x-axis, slope is minus b. So this explains the graph or the change in molar conductivity on dilution for strong electrolytes. The next thing we are going to learn is a very familiar one to you probably, that is Kohlrausch's law. Kohlrausch's law for independent migration of ions. Now to explain this, we have to go back to our asymmetric effect. Here we have already told or discussed about the ionic atmosphere present, and as we have told, because of the strong attraction already present inside the solution, it is a bit difficult for them to move towards their electrodes, whether it is positive or negative. So suppose if we are diluting this solution, what happens? Solvent molecules will actually come and take their places inside this, in between this. Okay, we see solvent molecules will come and try to place them in between these ions. So what happens is, obviously there will be a reduction in the attraction between positive and negative ions. So everywhere there is solvent molecules, or in effect the total number of solvent molecules have been increased. So they will obviously find some space between this, they will interfere with the ionic atmosphere, and the effect or the intensity of attraction between positive and negative charge or positive and negative ions within the solution decreases. Because of this, what happens? The ions migration towards the electrodes, towards the both electrodes, will actually be easier than before. So because of dilution, I'll just write it here. So because of dilution, what are the changes happening? So when dilution increases, number of solvent molecules increases. This will cause a decrease in strength of attraction or force of attraction between the ions. Therefore, it becomes easier for them to move towards their potentials, opposite potentials. So the ease of their migration, you can say it as migration, will obviously increase. Okay, so because of dilution, in simple words, it is easy for the ions to migrate towards their oppositely charged electrodes. Now, as we dilute more and more, that means we become, or we finally reach at the infinite dilution. At this point, we can say that there is little or no force of attraction between those ions. So when we are at infinite dilution, which is actually a kind of hypothetical case, we can say. So at infinite dilution, our system is going to be looking something like this. So in a system, I have positive charge, which is supposed to be surrounded by negative charges. However, I'm going to get only solvent molecules around it completely. So obviously it is very much shielded from the negative charges, right? So because of this, there is little or no force of attraction between the positive and negative ions. Hence, their migration towards the electrodes from attaching a positive charge and a negative charge. The migration of the positive towards the negative and the negative ions towards the positive electrode does not depend on the counterpart ions, which means in earlier case, my migration towards the negative or positive electrode of the ions actually dependent on the opposite ion. That means if I am considering the positive charge, their migration was dependent on the negative charge around them. But now, since there is no much attraction between them, we can call it as, or the migration can be called as independent migration, or migration that is not dependent on the coions. So according to Cauchy-Riesch's law, we say that now migration of ions, any ions, is independent on coions because there is no force or attraction between them. This happens only at infinite dilution. So we have to mention at lambda 0 m. So if their migration are independent of one another, in that case, I can write molar conductivity of anion and molar conductivity of cation separately, right? Which means I will be able to write Suppose I have an electrolyte, say AB, which is dissociating into A plus and B minus. Okay, so molar conductivity at infinite dilution for AB can be written as sum of molar conductivity at infinite dilution for A plus molar conductivity at infinite dilution for B minus. Because they are independent of each other, they can be summed separately. This is what actually Kohlrausch's law of independent migration of ions explain. For example, if I consider sodium chloride, which is a strong electrolyte, it will dissociate into Na plus and Cl minus. So molar conductivity at infinite dilution for sodium chloride can be found from molar conductivity at infinite dilution for sodium ion plus that of chloride ion. Okay, and also this is especially useful only in case of strong electrolytes, because only for strong electrolytes we can find the lambda 0 m value by extrapolation. Okay, so as you know from this graph, or I'll show the graph where we can compare both simultaneously. This graph, from this it is evident that once you get this plot and you extrapolate this into this region, you will get lambda 0 m value for strong electrolytes. But for weak electrolytes, since it goes like this without even touching that region, it is difficult to find lambda 0 m value for weak electrolytes. But using that of strong electrolytes, it's actually possible to find for weak electrolytes also. But directly from the graph, it is not possible. And this comes as one of the application of Kohlrausch's law. So now let's look into the application. So the first use is to calculate the conductance of weak electrolyte at infinite dilution, or to calculate lambda 0 m value for weak electrolytes. So as I told, for strong electrolytes it's directly possible to find it from the graph, but for weak electrolytes we can make use of the values from strong electrolytes and also the Kohlrausch's law, and finally get into the lambda 0 m values. So let's take an example for weak electrolyte, that can be acetic acid, which is CH3COOH. And for acetic acid, what will be the lambda 0 m value for CH3COOH? Since it obeys Kohlrausch's law, it will be lambda 0 m CH3COO minus plus lambda 0 m of H plus. But the thing is, I do not know what is this and what is this value even from the graph, so I cannot find this particular value. But there is an indirect way to find that. For this, I need to consider any other electrolytes which have a... So suppose if I know the lambda 0 m values for any other 3 strong electrolytes or some strong electrolytes whose combination of ions can actually give me this ion combination. So I'll explain with an example. The first question to you is that is CH3COONA a strong electrolyte or a weak electrolyte? As you can see, CH3COONA, this is a salt formed from acetic acid and sodium hydroxide, CH3COOH and NaOH. Since we have already explained that any salt formed from strong acid and strong base is going to be a strong electrolyte. Similarly, any salt formed from strong acid and weak base, or weak acid and strong base, if any one of their parent is actually strong, in those cases they will be a strong electrolyte. If both are weak, then it is going to be a weak electrolyte. So this is actually a strong electrolyte. So in general, salts of weak acid, strong base, strong acid, weak base, strong acid, strong base. these three are going to be strong electrolytes, and that of weak acid and weak base is actually a weak electrolyte. Weak acid and weak base will constitute weak electrolyte. Now, to find that of acetic acid, I will consider the lambda 0m values for sodium acetate CH3COONA, that will be equal to lambda 0m of CH3COO minus plus lambda 0m for Na plus. Since it is a strong electrolyte, I will know the value of lambda 0m value for this particular thing. Now the next thing I would need is lambda 0m value of HCl. Why HCl? Because from this I will get lambda 0m of H plus, which I actually need to find that of acetic acid. Okay, so this is going to be lambda 0m of H plus plus lambda 0m of Cl minus. Now if I add them up, what do I get? If I add both of this, I'll have lambda 0m of CH3COO minus plus lambda 0m of Na plus lambda 0m of H plus lambda 0m of Cl minus. Now if I look carefully to get this both, that is CH3COO minus and H plus, that is obviously present here, and H plus. But from that I actually should subtract these two terms. Okay, these two terms are actually unwanted here, so I have to take them away. So if you look at this, it is Na plus and Cl minus. So if I try to subtract the molar conductivity at infinite dilution for sodium chloride from this equation, in that case I am going to get only that required for CH3CO minus and H plus. So next is for lambda 0m value for NaCl, which will be equal to lambda 0m value for Na plus lambda 0m value for Cl minus. So this equation is what I'm going to subtract from these two. So let's name this one as 1, 2 and 3. So what are we going to do? We are going to do 1 plus 2 minus 3. So that will be lambda 0m for CH3COONA, which I will be getting from the graph, plus lambda 0m for HCl. Again I will be getting by extrapolating the graph, because they are both strong electrolytes. And finally for NaCl, again another strong electrolyte, which I will be getting by extrapolating its graph. Now the sum of these three, their LHS will be lambda 0m CH3COO minus plus lambda 0m H plus, first let's write Na plus lambda 0m H plus lambda 0m Cl minus sorry, this has to be minus because we're subtracting it from the other two, minus lambda 0m for Na plus minus lambda 0m for Cl minus. So similar terms can be cancelled out, Na plus, Cl minus. So what is left? So what is left is just what is actually required for acetic acid, which means this is lambda 0m CH3COO minus plus lambda 0m H plus, or I can write this is actually equal to lambda 0m for CH3COOH, which is a weak electrolyte. So therefore, from the lambda 0 m values for strong electrolytes, 3 different strong electrolyte, using their common ions, we have found the lambda 0 m value for a weak electrolyte. And this is for the first application for Cauler-Rash's law. Now let's look at the second application. That is to calculate alpha or degree of dissociation. To calculate alpha, that is the degree of dissociation. For that, we are using a particular equation. Alpha is equal to lambda m divided by lambda 0 m. Lambda m actually represents the number of ions present in a solution at a time. Present in any solution. So what does lambda 0 m represent? This is actually, since it is an infinite dilution, we know that complete dissociation takes place and the maximum number of ions possible will be there in the solution at the time of infinite dilution. So this is maximum number of ions present. So this ratio will actually give you alpha, and that is the second application. Problem on this topic. So the question is, you need to find which of the formula will give lambda 0 m value for CH3COOH. Given that lambda 0 m value for CH3COONA is equal to A. That is equal to A. Lambda 0 m value for HCl is equal to B. Lambda 0 m value for KCl is equal to C. Lambda 0 m value for Na2SO4 is equal to D. And finally, lambda 0 m value for K2SO4 is equal to E. So on rearranging these formulas, that means you have to compare their ions, cancel out the common ions, and then you have to find what is the correct formula that will give correct formula in terms of A, B, C, D and E, which will give me lambda 0 m for CH3COOH. Since there are many ions involved here, that is almost 10 ions are involved here, but we need to cancel out everything and finally get only 2 ions. It will be a bit confusing, but the only way, or the simple way, is to firstly write down all the ions possible. So I need to get this, what I need to get is CH3COO minus and H plus. Now I am going to write down only the ions possible. So they will be CH3COO minus and Na plus. In here it will be H plus Cl minus, K plus Cl minus, 2Na plus. The stoichiometric or the number of every atom should definitely be represented as the stoichiometric coefficient. So Na2 will be dissociating into 2Na plus. SO4 2 minus, K2SO4 will be 2K plus and again SO4 2 minus. So now since I want CH3CO minus and H plus, I will have to add both of them. Okay, so I will add these both equations. But from that I need to subtract Na plus and also Cl minus. To subtract Cl minus, from this equation I will subtract this particular equation. When I subtract, and unwantedly K plus is being subtracted. So because of that, to nullify the effect of a minus K plus, I will have to add a K plus. So to this equation I will actually add this particular equation. Okay. But there is a difference in the stoichiometry also, that I will have to do it accordingly. Now when I add this K plus equation, there is unwantedly a sulfate being added. To subtract that, I will subtract this particular equation from that. Okay, this is the way I'll be doing. I'll just have to subtract the second last equation from the overall equation I got now to subtract that sulfate ion. Now Na plus can also be subtracted from the last equation that we have used. Now let's try to establish that. Firstly, I had to add CH3COO minus plus Na plus with H plus and Cl minus. Then I have to subtract KCl from that, minus K plus and Cl minus. Unwantedly a K plus is being added, so again I'll have to add to this 2K plus SO4 2 minus. But I need to subtract sulfate from that, so minus 2Na plus minus SO4 2 minus. Okay, but somewhere you can see there is, I'll put brackets everywhere so that it is clear, or just instead of bracket you can mark them like this. Brackets cause a change in sign, which is again difficult. So at some places there is actually a stoichiometric coefficient of 2. For example, for K plus we have that. If we have it for K plus, then I have to put a 2 here also. For that I will have to multiply the entire term KCl with 2. So this term for KCl, this has to be multiplied with 2. So if I multiply with 2, K plus also gets a 2, Cl minus also gets a 2. But in the H plus and Cl minus, I have only one Cl minus. That should also become 2. Here also 2, here also 2. So that means this equation also multiplied by 2. Okay, done. Next, if you see, so what did I cancel out here now? I was able to cancel out 2K plus, 2K plus, 2Cl minus, 2Cl minus. Now the sulfate if I see, they're also same. Now I have only Na plus pentene, but for Na plus, the problem is 2 Na plus and 1 Na plus. So that 1 Na plus I have to convert it into 2 Na plus, and that has come from the CH3COO minus Na plus combination. So that both should be multiplied by 2. Okay, so here also I have to put a 2. Now if I see, I have Na plus also cancelled out. So what is left now? I have 2CH3COO minus plus 2H plus. But what I want is not for 2 ions but just for a single ion, which means I will have to half whatever I have got. So I have to multiply half into this one. Okay. So in terms of A, B, C, D and E, if I check, I'll see that I added A plus B. So it is A plus B, and from that I subtracted C minus C. From that again I added E. To that I added E and subtracted D. Okay, but somewhere I had to multiply with 2. Those places I put a 2 also. A has been multiplied by 2, B has been multiplied by 2 and C also. So 2A, 2B, 2C. We'll have 2A plus 2B minus 2C. And the entire thing should be halved. So my final answer is half into 2A plus 2B plus minus 2C plus E minus D. This is how it is going to be. Okay, this is the final answer. Hope that does not make any confusion. You just have to write down what are the ions involved and in what way you can cancel out everything to get only the 2 ions that is required. And remember, the stoichiometry should be always 1 because you need CH3COO minus and H plus. By getting 2 CH3COO minus plus 2 H plus, that is not enough. That should be halved so that you will get only single ion species. So that are the applications of Caulerash's law.